Cyclic compounds play a hugely important role in organic synthesis, and many reactions that involve the synthesis of commercially pharmaceutically useful compounds involves the creation of a ring. Sometimes they are large ring compounds and we call those macrocycles, and sometimes it's the synthesis of molecules that include cycles in their structure, and we call those polycyclic molecules. In the synthesis of polycyclic molecules, which is what I'm going to discuss in the next few slides, the cyclic molecule acts as a template. So there is an initial cycle in which all the rings are built onto, and we call that annulation. And you might remember, for example, we have looked at annulation processing in previous videos. For example, the Robinson annulation that we discussed previously. There's something called the Baldwin's rules for ring closure. They were published by Baldwin. He is a British chemist in the mid-70s, and his paper at the time was one of the most, I think it was the most cited, among the most cited in the year it was published, 1976, I think. Although they're called Baldwin's rules, I think they would be better called Baldwin's guidelines. And there are a set of guidelines that predict what sort of ring will be formed in a chemical reaction that involves a ring closure. And they are based on the stereochemical requirements of the reagent and the substrate, and also the angles of approach that are allowed when the two reactive centers that are going to close the ring come together. So to form a ring, the two reactive centers are connected by a tether or atoms, typically, or not, although not always, carbon. So you have a series of atoms, and your X and your Y, the two reactive centers that are going to close the ring, attach. There are constraints on which angles those two reactive centers can approach one another, and that will determine the stereochemistry of the product. Another thing that it will influence how those two reactive centers are going to approach is the length and the nature of the tether. And whether it will allow that particular approach to be attained. So if the length and nature of the tether is such that will allow those two reactive centers to come together, the ring is more likely to form. If that geometry cannot be attained, then the ring formation is difficult. It's a disfavored process. It's not that it's not going to happen, but it won't happen fast enough. So if there are alternative reactions that can happen that are more favorable, that are faster, the ring will not form, and those competitive reactions will take place. You can still form the ring even if it's disfavored, if there are no alternate reactions that can compete. So that's what I'm saying. There are not so much rules as a set of guidelines. There are a set of guidelines that suggest whether a particular ring of a particular structure will form or not. So it will determine which are the most favored rings when you have that particular chain of atoms, and which ones are disfavored. The ones that, if there are other possible reactions that can take place that compete with the ring formation, those will take precedent and the ring will not form. There are a few words that we need to get familiar with when looking at Baldwin's rules before deciding if a particular ring formation will be favorable or not favorable. Baldwin classified reactions with respect to different things. One was the electron flow. He talked about exorings, and in exorings, the electron flow of the reaction is external to the ring form. And endorings, the electron flow is within the ring that is being formed. So you have exo, electron flow outside to the ring, endo, electron flow is within the ring being formed. And then he also classified the reactions, the cyclization reactions, depending on the atom that is being attacked. So a TET reaction, if the atom being attacked is an sp3 atom, trig, if the attack happens on an sp2 atom, and dig if the attack happens on an sp atom. So for example, here the attack is in an sp2 atom, so this is a trig cyclization, and the electron flow is the way the electrons move when the reaction takes place means that the electrons are within the ring being formed. So this particular example would be an example of an endo-trig cyclization reaction. What about this one? Well, if you see the electron flow when the reaction takes place is outside the ring being formed, they end up here. So this is an exo reaction. And it's a trig reaction because the attack happens on an sp2 atom. So this would be an example of an exotrig cyclization reaction. So I'm going to ask you to stop the video for a few minutes, have a look at this particular reaction, and describe, using Baldwin's nomenclature, what sort of ring closure you are showing. So stop the video now. I hope you stop the video and have a go at the exercise. So first of all, is it an exo or an endo ring? Well, the electron flow in this case is very much outside the final ring form. So I would say that this is an exo ring. And the attack happens on an sp3 atom, so that this would be an exotet ring closing process. And finally, I'm going to ask you again to stop the video for a few minutes, have a look at this particular ring closure example of a ring closing reaction, and describe it using Baldwin's nomenclature. Stop the video now, please. So if we look first, for example, at the flow of electrons, in this case you can see that the electron flow is very much out of the new ring being formed. So this would be an exo reaction. And the attack happens on an sp atom. This is an alkyne. So that's a dig attack. So this would be an exo-dig reaction. As you can see, with exo and endo and tet, trig and dig, you can describe in general terms what type of reaction you are going to produce. Baldwin's rules from ring closure. Well, it is possible to describe ring forming reactions by the number of atoms in the cyclic product, so 3, 4, 5, 6, 7, whether the reaction is exo or endo, and whether it involves an attack on sp3, sp2, or sp atom, a tet, trig, or dig attack. So for example, here you've got the 3 examples of 3 reactions that result in the formation of a 5-member ring. And for example, this one is this specifically one is an exo reaction, and the attack happens in an sp3 atom, so it's a 5-exotet reaction. The one in the middle, the attack again is an exo attack. The electron flow is outside of the final ring being formed, but the attack is an sp2 atom, it's an alkene, so this is a 5-exotrig reaction. And finally, the following, in the final example, the flow of the electrons is inside the ring being formed, so it's an endo reaction. Again, 5 because you end up with a 5-member ring, and dig because the attack happens on an sp atom. So it's just a simple way of describing the cycle that is being formed, depending on whether the electrons flow inside or outside the ring, the number of members of the ring, and whether the attack happens in an sp3, sp2, or sp atom.